Welcome to Lesson 10, One-Way Analysis of Variance. This is also known as a one-way ANOVA. Your first question is probably, what is a one-way ANOVA? A one-way ANOVA compares the means of three or more independent groups. Last week, you learned about independent means t-tests, which compare the means of two independent groups. An ANOVA is an extension of that. This week, you're going to be comparing three or more independent groups in terms of their means. Another common question is why not multiple independent t-tests? So why should we do a one-way ANOVA as opposed to doing a series of independent t-tests for all the possible pairs? Well, multiple tests result in inflated alpha and a greater chance of making a type 1 error. So recall from back in Lesson 8, a type 1 error is when you reject the null hypothesis when the null hypothesis is really true. If you're doing multiple independent t-tests or multiple statistical analyses of any type really, the actual alpha rate is being inflated. So if you're doing, for example, 3 different tests and you're setting alpha to 0.05 for each of those 3 tests, by the time that you do 3 tests, the actual alpha level is much greater. It's a little bit less than 0.15 if you're doing 3 different tests. So we use a one-way ANOVA so that the actual overall alpha level really is 0.05 and it's not inflated from doing multiple tests. 2 key topics that we're going to cover in this presentation. First, the 5-step hypothesis testing procedure using Minitab Express. You are not going to be conducting one-way ANOVAs by hand. So you're not going to be computing these test statistics by hand. You will always be using Minitab Express, or you'll be given the relevant Minitab Express output. And second, pairwise comparisons. So a one-way ANOVA is what we call an omnibus test. It will tell you whether or not there's a significant difference overall, but if there is a significant difference, it won't tell you where those differences lie. So it won't tell you exactly what pairs are different from one another. In those cases, we need to make pairwise comparisons. So let's start by looking at the 5-step hypothesis testing procedure for our one-way ANOVA. Step 1, check assumptions and write hypotheses. The assumptions of a one-way ANOVA are that the samples are independent, just like when you did the independent means t-test last week with the one-way ANOVA. All of your groups need to be independent from one another. The response variable is approximately normally distributed. And population variances are all approximately equal. To check this last assumption, we're going to look at the sample standard deviations. If the largest standard deviation is not more than twice of the smallest standard deviation, then this assumption has been met. Now, there's a number of different ways to check for what we call homogeneity of variances, in other words, equal variances across groups in the population. This is the method that we're going to be using because it's one of the simplest and the most straightforward. You're just going to compute sample standard deviations and compare them using this rule. Writing hypotheses. Recall the null hypothesis always contains the equalities. So the null hypothesis for a one-way ANOVA is that all of the population means are equal. The alternative hypothesis is that not all population means are equal. Step 2, test statistic. In this course, you're going to be using Minitab Express to obtain the F test statistic. Similarly, for step 3, p-value, we're going to use Minitab Express to obtain the p-value. Step 4, make decision. As always, if p is greater than alpha, you fail to reject the null hypothesis. If p is less than or equal to alpha, you reject the null hypothesis. And step 5, state real-world conclusion. Again, based on your decision in step 4, state your conclusion in relation to the original research question. Let's go through one example. Here's our research question. Do students who prefer to watch running, swimming, and volleyball on television differ in terms of how many hours per week they watch television? We're told to assume that hours per week watching television is approximately normally distributed in the population, These data were collected from a representative sample of Stat 200 students at the beginning of the summer 2016 semester. So let's start going through the 5-step hypothesis testing procedure. Step 1, our assumptions are that the samples are independent. In this case, they are. There were different students who said that they preferred each of the 3 different sports. The response variable is approximately normally distributed. We are told in this scenario to assume that number of hours watching television is normally distributed in the population, so this assumption has been met. And finally, population variances are all approximately equal. Recall, we're going to check this assumption by looking at the sample standard deviations. So let's go to Minitab Express and compute the sample standard deviations for the 3 groups. When you run a one-way ANOVA in Minitab Express, you'll get the descriptive statistics. So what I'm going to do here is I'm going to run the one-way ANOVA. Our response variable is hours spent watching television per week. The factor is favorite summer sport. When I click OK, we can scroll down, and here in the means table, we're given the mean and standard deviation for each of the 3 groups. The smallest standard deviation is 15.1793. The largest is 22.515. So the largest standard deviation is not more than twice of the smallest standard deviation. So this assumption has been met. The next step is to write our hypotheses. The null hypothesis is that all of the population means are equal. So the mean for the students who prefer running is equal to the mean for the students who prefer swimming and equal to the mean for the students who prefer volleyball. The alternative hypothesis is that not all population means are equal. Step 2 to compute the test statistic, and step 3 to compute the p-value, we're going to perform in Minitab Express. We already have this output. Here in our analysis of variance table, we're given our F test statistic to be 0.25 and our p-value to be 0.7773. So here we have step 2 and step 3 of the 5-step hypothesis testing procedure. Step 4 is to make a decision. In this case, our p-value is 0.7773. This is greater than the standard alpha level of 0.05, so we failed to reject the null hypothesis. In step 5, state real-world conclusion. Recall our original research question. Also recall that we failed to reject the null hypothesis. So our conclusion in terms of this original research question is no, there is not evidence that students who prefer to watch running, swimming, and volleyball on television differ in terms of how many hours per week they watch television. So the results are said to be not statistically significant. There is no statistically significant difference between these groups. Now, let's move on to pairwise comparisons. Typically, we only conduct pairwise comparisons if the overall one-way ANOVA is statistically significant. So in the last example, where we failed to reject the null hypothesis and we said there was not a statistically significant difference, in that case, we probably would not conduct pairwise comparisons. We typically only conduct pairwise comparisons when the results are statistically significant, because the pairwise comparisons will tell you where those statistically significant differences are, so which groups are different from one another. Again, if we want to know which pairs of samples are different, we need to do pairwise comparisons. These are also known as post hoc tests because they're performed after the overall one-way ANOVA. In this course, we're going to be using the Tukey method. The Tukey method makes all possible pairwise comparisons. For each pairwise comparison, the null hypothesis is that the mean of group 1 minus the mean of group 2 equals 0. In other words, the 2 population means are equal. The alternative hypothesis is that the mean of group 1 minus the mean of group 2 does not equal 0. In other words, the 2 population means are not equal. Let's walk through one example. Here's our research question. Do students who prefer different winter sports, figure skating, ice hockey, or curling, differ in terms of their heights? Assume that height is normally distributed in the population, and we're going to be working with data that were collected at the beginning of the spring 2016 semester from Stat 200 students. The first step is to conduct the overall one-way ANOVA. We'll check assumptions. All samples are independent. Yes, we have 3 independent groups. There were different students who said that they prefer each of those 3 different sports. The response variable is approximately normally distributed. Yes, we're told in this scenario to assume that it is normally distributed. And population variances are all approximately equal. Recall we're going to look at the sample standard deviations from the means table in the output in Minitab Express. Here, the smallest standard deviation is 3.8633. The largest is 3.9464. The largest is not more than twice of the smallest standard deviation, so this assumption has been met. Next, we write our hypotheses. The null hypothesis is that all of the population means are equal. The alternative hypothesis is that not all population means are equal. Step 2 is to compute the test statistic. Here we have our analysis of variance table from Minitab Express. The F value, or F test statistic, is 36.31. Step 3 is to find the p-value, which is less than 0.0001. Step 4, make a decision. Our p-value is less than 0.0001, which is less than the standard alpha level of 0.05, so we reject the null hypothesis. Step 5, state conclusion. There is evidence that the mean heights of the 3 groups are not all equal. Note, however, that this only tells us that overall there is some difference between these groups. In other words, the means of the 3 groups are not all equal. It does not tell us exactly which pairs are different from one another. In order to determine which pairs are different, we need to conduct a pairwise comparisons test. When you're conducting a one-way ANOVA in Minitab Express, you can request Tukey output. When you request the Tukey output, so a Tukey post-hoc test, you'll get 2 different pieces of output. The first is this table titled Grouping Information Using the Tukey Method and 95% Confidence. In this table, any groups that do not share a letter are significantly different from one another. Groups that share a letter are not significantly different from one another. So in this table, curling and ice hockey both share the letter A. They're both in group A. That means that they are not significantly different from one another. Curling and figure skating do not share a letter. Curling is only in group A, figure skating is only in group B, so these 2 groups are significantly different from one another. Ice hockey and figure skating do not share a letter, so they are also significantly different from one another. So that's the first piece of output if you request a Tukey post-hoc test in Minitab Express. The second table that you'll get is titled Tukey Simultaneous Tests for Differences in Means. This will tell you the difference in the means between the 2 groups, the standard error of that difference, a 95% confidence interval for that difference, and this 95% confidence interval is adjusted for the fact that we're conducting 3 different simultaneous tests here. A t-value, which is the t-test statistic for this comparison, and the adjusted p-value. We can use this adjusted p-value to determine which pairs are statistically significantly different from one another. If an adjusted p-value is less than or equal to 0.05, then those 2 groups are significantly different. For example here, figure skating and curling, the adjusted p-value is less than 0.0001, so we would reject the null hypothesis and say that figure skating and curling are significantly different. Ice hockey and curling, the p-value is 0.4346, which is greater than 0.05. So we would fail to reject the null hypothesis and say that there is not a difference between ice hockey and curling. And ice hockey and figure skating have an adjusted p-value less than 0.0001. So we would reject the null hypothesis and conclude that ice hockey and figure skating are significantly different from one another. Note that the results that we got using these adjusted p-values are the same as the results that we had earlier when we were using the grouping information from the first table. So to review, the key topics that you'll want to focus on this week, you need to understand why not multiple independent t-tests. So why do we use a one-way ANOVA instead of doing a series of independent t-tests? The five-step hypothesis testing procedure. We saw two quick examples here. There's a number of examples in your notes this week as well. Note that this is the same five-step hypothesis testing procedure that you've been using since lesson 8. And finally, pairwise comparisons. A one-way ANOVA is known as an omnibus test, so it only tells you if there's a difference overall. In order to know which pairs are different from one another, you need to conduct pairwise comparisons tests. In this course, we're going to be using Tukey. I strongly suggest that you also go back and review lesson 8 this week. The concepts of error, power, and p-values are the same for all hypothesis tests, and those concepts, specifically type 1 and type 2 error, statistical power, and the meaning of p-values, are going to come up in each of the remaining lessons this semester. As always, if you have any questions as you're working through this week's materials, please post them to the Lesson 10 discussion board on Canvas.